Okay, so let me leave. Zoom, can you hear me? I just left like my personal um, account on the Zoom meeting. Can you hear me?
Yes, we can hear you.
Okay, all right. So you can see the screen, right? We're going to do supervised representation. Okay. So yeah, okay. So this class will be all about channeling whatever you learned in this class, and you will be challenged in a different way today, just like how you were with ICA. We're going to go over another method called CCA. Some of you have a statistics background. Have you heard of CCA? CCA? Whoever is in statistics will know this. Like who has a statistics major, they probably used it in their assignments. No? Okay. There's like an Excel function too for CCA. CCA, what it tries to do is model the cross correlation between two variables. Surprisingly, we have not done that yet. We're going to do that today. You guys have been more focused on like linear regression and other kinds of spaces. So let's go into detail. So right now, here's what we've learned, right? We've learned the basic ways to represent data, like Fourier wavelet type basis, which does not really, it's independent of the characteristics of the data. It's like just an equation, you plug it in, no need to consider data. It can vary as much as it wants. Now, here are the ones that you've used the most: PCA, NMF, ICA. It tries to emphasize different techniques or different aspects of the data. Do people represent what PCA remember, not represent? Do people remember what PCA did?
To maximize the amount of energy that's captured within like X amount of something.
What's another way of saying that? Like a mathematical term. Maximize variance, right? And PCA, one weakness of it is that it assumes things are on an underlying linear plane, right? NMF, that one, what was in NMF? Do you guys remember? No, yeah, but what more than that? What is it doing?
So represents
So it's like a playing field, right? If you play football, like soccer, the ball can't go to the crowd. So people push it back. Same with cricket, right? So same thing with NMF. You're in a constrained playing field. The minute you go outside of that cone, it gets projected back, right? So that's NMF. ICA, I lectured that, so you shouldn't forget. What is ICA?
shows a model such that the components.
Yeah, so like the cocktail party problem, people are all talking, but I'm not related to your voice or his voice. Everyone's voice is independent. So you have to hit it with a matrix that ICA will provide that separates the independent sounds. In homework 2, you guys used ICA, if you remember. So now this was data specific, but what if we want bases that are both data specific and task specific? So we'll give an example. Like I just said, PCA is for maximum variance. Overcomplete bases preserve the sparsity, right? And then NMF and ICA are in that. So let's go over a problem right now. Classification, right? So we have input data X, and we want to assign a class Y, right? So that sounds like everything you've done at CMU, right? You want to find some representation of X that best captures the inherent characteristics of X, and then you want to predict Y from the X. So let's get into it. This is obviously called supervised learning, right? Because you have a label here. So when you have a label, then it's a lot easier. You don't need to manually create the label. It's already there for you. So the task is creating the one-to-one relation between feature vector and label. So what was like one task, one way to do this? You all probably learned it. Regression, right? Regression is one way to do this. Or even like a neural network, which is banned in this course. That's a good way to do this, right? So a lot of things do this, even like y equals mx plus b, right? That's just this. You have an input x and you get assigned output y, and then you make a label based on that. So basis that maximizes shared information with another view. Yeah, so we'll get into that. So now let's look at this example, right? There's a robot. He's firing arrows at the target, and we don't know how the wind will affect the movement. So if you're an expert archer, you will not shoot straight, right? You'll shoot a little above because you know the gravity will point the arrow down. So you want to take that into account when you're shooting the arrow. And even robots need to know that. So we can just naively, right? We can measure the wind in 3 directions because we live in a 3D world. And the offset, you don't need to consider the 3rd dimension, just the 2nd dimension, because the arrow is on the target. So you need to know x, y, how far it is from the target. So like this arrow is far from the target. This arrow is near the target. So you can easily do this just with the methods you know, right? Find the feature vector x, like x is the wind speed, xi is the wind speed, and yi is the offset, right? So you have a wind speed feature vector and offset label, 2-dimensional label, and you can collect them. And you can do the optimization. I think this should be xtx. This is one of the forms, right? You guys remember xtx inverse xty? This is, I think, another form of it. It's the same thing. So you can do the regression. This is the beta coefficients that minimize the loss function. So this is what you already thought, right?
Yeah.
This is already like, yeah, pseudo inverse is already what you like learned. But if you really wanted to think about it, right? A lot of times when you collect data, only some dimensions matter. So like somebody can say that not everything in the x position, x vector matters, just a small slice of it. So we can put some ut that will extract just some parts of the x that really matter. And same thing with y hat. So instead of working with x and y like alone, picture x and y are huge, right? We can just say that let's just take out a subset of x and a subset of y. So this is where CCA comes in. We want to find a projection of wind vector x and a projection of arrow location y, so that we can predict the projection. And what this is trying to do is we're trying to capture the cross correlation between x and y, right? It's not just like we're predicting y from x. We're trying to see, okay, here's how y is, here's how x is. Now we have to see the inner joint relationship between the two. This is what CCA tries to do. When you see the equations of CCA, it'll make more sense to you. Let's see, direction of max correlation ignores parts of wind. Yeah, this is saying the same thing. So some of you might think, why not just jointly analyze, right? Like, let's just combine the x and the y together and just do like PCA on that. But PCA, what it does is it will decorrelate all the variables. We don't want that. We want to find the cross correlation between x and y. So like picture x is one cluster, y is one cluster, and you want to find the strength between the two. Like what is it? Because everything is correlated in some way. Like even if it's a weak correlation, what is like the correlation between both x and y? No, we will assume that variables have some cross correlation. Cross correlation is just between X and Y. So yeah, just think of it like CXY, C underscore XY. That's cross correlation. So here are the terms. You already know this. CXX is 1 over N XXT. You did this in your homework. Sorry? These are just equations you've used. Oh, you're talking about the objective. We'll get into that. Yeah. Okay, so this is the formal equation for the cross correlation. You already know this, XY transpose over N. But like I said before, we just want to consider some part of it because maybe we have like memory limitation. We're just going to do UTX, VTY. So picture that X hat is like, you even saw this in SVD, right? Like when you did SVD, only like, I think when you saw that curve, it flattened out, right? At some point, you guys remember? The, what's it called? The KLE curve, it like flattened. So that means that just a part of it mattered. After it flattens, you don't need to consider anymore. So same thing here. You don't need to consider the whole X, just consider a part of it. So that's what the UT and VT are trying to do. It's just truncating the most important ones, important columns. You can think of it like that. Okay, I know I'm going very fast and this lecture will probably end early, but I will just do my best here. So like I said before, someone want to ask with the objective. We want to maximize this cross correlation, C X hat, Y hat, right? And we want to find the U and the V that basically maximize that to the best ability. So yeah, that's the equation. So I'm going to stop here. Is there any like question? All we're doing is we're maximizing the cross correlation. We never really looked at cross correlation in our previous methods. Does the objective make sense to people? Like
actions, which X
I don't know about that. We're finding the like the strength, kind of like picture two clusters and the like middle between the two. We're trying to measure that in some numerical way. It's like that. It's between two variables. So it's not just like one cluster diagonal that you see all the time. It's like, we'll get into it, yeah. So do people like see the point? Like PCA did not do this, right? PCA just found the maximal variance. This is a different objective. Okay, so always, if U and V are not constrained, then you can have infinite solution. We saw that in the EM algorithm, that if W are not one length, it could be anything. So we have to constrain it. And then we also have to whiten X and whiten Y. Do people remember whitening? Like whitening was when we took the, it's like the, what's it called? Remember that upside down V to the -1/2? So that basically what it did is it, that's whitening, that part. That made the variance 1 for everything, every variable. So whitening is important because if we don't have that constraint, then X and Y can be large. Like to give an example, if somebody says their height, somebody might say 5 feet, or somebody might say 160 centimeters or something. Or yeah, something like that. Yeah. So they both represent the same thing, but since they're not whitened, it will think that X is large, the 161 is large. So you have to enforce whitening to make sure that the variance is 1. It's like making the, it's like standardizing a column. Like That way, there is no ambiguity between one variable and another. And then U and V, we already know, they have to be orthonormal. Okay, so I think you guys know this. If you linearity of expectation, this thing will switch. So you'll get UT CXXU. Let me see, because UTX will be here, and then XTU will be here. So then you'll get this, because the transpose will flip the order. So here is the full form. We want to argmax CXY and get the UV that maximize it, such that the UTU of the single correlation is in identity, and cross correlation of Y single is also I. So this is canonical correlation analysis. So we have a problem, right? Because maximizing a matrix is not really a practical thing to do. So how do you think we go about this problem? You guys did it in homework 1, if you remember. No. Like, you didn't maximize it, but you used this operation on a matrix that essentially maximizes the matrix. Whoever did the bonus will know. Yeah, what is that called? No. A trace, right? The trace of a matrix, it's the sum of the diagonal. The reason this works is, you guys remember that a determinant of a matrix is the multiplication of the diagonal, right? When it's in the row echelon form. So same thing here. You can maximize a matrix by maximizing the trace. So these two are equivalent. So this works out, right? Because a trace is a sum of variables. So you can do that. It's not like you're considering a grid of possibilities. So if we maximize the sum of the diagonals of the cross correlation matrix, then we maximize the sum of the eigenvalues of the cross correlation matrix. Okay. Because we're dealing with CXY. So that's why we're dealing with, if we maximize the diagonal, then we'll automatically get the eigenvalue solution. So here's pole 1. Exactly. That's why I just maximize the trace. The last one is correct, by the way. It's ambiguous. The link is MLSP23, like tinyurl.com, MLSP23 11.16.1. If you have trouble loading, you can speak up. So I'll repeat it, tinyurl.com/MLSP23 -1116-1.
So that is like a
Let me see this one. It's a good medium.
yeah, it sounds better.
Are people on Zoom able to access the poll? Just speak up. I can't see the text.
Yes.
Yes. So,
Okay, also, I'll just say it now. Some of you guys had issues with homework 2 grading. So just come to me after class. I'll just get it resolved today. Even on Zoom, just join the Zoom link. Okay, let's go into it. So only the third is wrong. Everything else is correct. You can use the pseudo inverse, right? That's optimizing the ridge regression, kernel ridge regression, all that. We went over this. This is all data-driven bases. And yeah, you can always use the trace to maximize a matrix. And the third, fourth, fifth one is ambiguous, so it's correct. Okay. So, okay. I think somebody asked about this. This is a good way of modeling the problem. CCA basically wants to extract the correlated subspace of X and Y from the noise. So basically, another way to think about it is the strength between two variables, like what can they both combined have to offer? That is like how you can think of CCA. So a lot of times you have two like data streams or two data sets, but they come from the same source. So like to give an example, maybe two audio transcriptions from the same movie or two stocks from the same stock market. So view one tries to capture the source and view two tries to capture the source. And you want to see how view one and view two have together. They're from the same source. If they're from different sources, then they're not correlated at all, right? Because they're different sources. So like an example, look at stocks from different parts of the economy. They're from the same economy, but they might have some correlated strength between the two, or multiple speakers saying the same thing. So let's visit the least squares formula, right? You already know this. This is the Frobenius norm error equation. So if we plug in our predicted and accepted value in this one, we'll get UTX minus VTY. UTX is the computed value. VTY is the predicted value. And this is what CCA is trying to do, is minimize these two given these two constraints. And yeah, this is CXX, right? XXT by YT. So let's try to solve it, right? You can this is the same thing as saying this. The Frobenius norm of the matrix inputs, you can just say it's trace of A, like the matrix times matrix transform. Then you can expand it. And then if you look, these two, because when you do trace, the permutation doesn't matter. So the left two will be 2nk, and the right two, they're the same thing, right? So because the permutation is okay in the trace, the commutative property holds. So you will get two trace UT XYTV. So just trust me, it evaluates to that. And you can, if you want to minimize this, then you have to maximize the right term because that has a minus sign. So we can maximize that. And we have our constraints. So you can put the Lagrangian on that. And then this is basically CCA. So those who already had pre-existing knowledge of CCA, it can be done like this. You're trying to maximize this with these two constraints. Because we want this to be identity and we want this to be identity. Okay. Now this is a tricky part. So taking derivatives after a few manipulations, let's see. You will get these two. And then when you do that, you will get you'll get these two equations. Now, if you look at here, think about what it's doing, right? I'm going from X to Y, then back to X. That's what this one is doing. And then I'm going from Y to X to Y again. So it's like you're switching to another portal and coming back, and you're reporting some value. That's what these two are doing. So yeah, like I said, it's the eigenvectors for the correlation of the vector obtained by transforming X to Y and back to X. And then you normalize the local variance, and then you do the same thing for the other one. So keep these 2 points in mind. In PCA, the eigenvalues were the variances in the directions, right? This was the directions that maximized variance. In CCA, we have the eigenvalues of the squared correlations. So CCA are truly measuring like X to Y and then back to X. So you're getting the squared correlations in the canonical correlation direction. If you combine these two equations, you will get this. And then you have an eigenvalue problem. And we already know how to solve eigenvalue problems. And yeah, basically that. There's some fixes we have to do. Let me see. Okay, so obviously there can be some invertibility, like if the diagonals are 0. So you can diagonally load this. And then that's what this is. The auto covariances, you can add identity with some non-1 value. And then do people know Cholesky decomposition? It turns out that if you have a strictly positive covariance matrix, then you can make it in this form. And then you can do SVD because you have the properties. So yeah, just take pole 2. I think this is easy. They're both true. Yeah, we already went over this one. And CCA is basically finding the eigenvalues of the squared correlations. It's just np.linearc.norm, like square root of everything. These polls will be available like the whole day, so you can answer if you missed it. It's both true. Okay, I don't even know this, so I'll learn with you. Okay. So yeah, PCA, remember from ICA class, it will find the directions of the maximal direction, but CCA is not like that. It will find the correlated strength vectors. You can think about it like that. Okay, and then CCA can find the class distinctions while reducing dimensionality. So CCA is a dimensional reduction technique, like PCA, right? Same thing. And PCA, because it's on a linear manifold, we can't really trust it, right? It doesn't have this objective of distinguishing between classes. So PCA is unsupervised because we don't care about the labels, right? We just find the direction of greatest variance, and we don't really label good or bad information. So it's kind of like a blind thing, PCA, because you're looking at the global pool and just looking at that. It's kind of like an outlier can screw up PCA because you're looking at the global pool. But with CCA, it's supervised, and we look at the correlation strength. It's kind of like opposite of ICA, because ICA looks for the independence, CCA looks for the joint strength area. And if you guys have heard of LDA, CCA is like the same of that when there's labels involved. So, and CCA, there's only a point of doing CCA if you have a notch feeling, a strong feeling that there is some correlation between the two variables. CCA will explore that space fully. Okay, I don't even know this, but you can make it a Rayleigh quotient. And yeah, I guess this might be a quiz question. PCA is also the same when A and B are these two in this form. Okay, and then yeah, I mean, CCA basis is good for compressing data. And when you care about the joint representation, this is good. Okay, so I think the professor is better in this than me. But EEG signals, they are good for this because EEG are very noisy. So to kind of streamline it down, you can use CCA. Yeah, go ahead. That's a true point, yeah. So CCA removes the useless info because they're finding correlation. So it's like if somebody's, or not somebody, but if there's a noise added, then it will remove it. Okay, you can do poll 3. So the second one you all should know is false. And the first is true. Yeah. Okay, so I think we can just go over LDA really fast. LDA, I'll just show you. I think there's a depiction here that will really explain it well. So let me show it. Yeah, this one. So in PCA, you guys try to find the variance, but look at LDA, right? It tries to see the two different distributions, and it maximizes the mean separation and minimizes the variance separation. So LDA has a different objective, right? It's trying to find the two close mean points that have that describe the data, whereas PCA is just caring about variance. LDA is like has another objective. So if we assume classes are Gaussian, then we can measure the compact clusters. So yeah, it's like two distributions that are describing the data, and we're minimizing the gap between the two. So we have this point metric within class scatter and between class scatter. So within is obviously within the distribution. Between is from opposites. So you want to minimize how far points can stay away from the mean, and you want to maximize the variance of the class means. Okay, so I said it wrong. we want to maximize the distance between means and minimize the distance the points have from each other. So small within class variance and high between class variance, and we maximize the ratio of the two. So, okay. So yeah, we can formulate like this. Same thing as the CCA. We have the true SW, but we can do it like this: WTSTW, WTSTB. And this is the scatter between all the points. So, yep. And then, yeah, this is just proving that it's the same thing as CCA. So LDA fails. I think let's go over this because this will be in your, I think, quiz. When classes do not fit into the model of a blob, then yeah, it won't be compact. We assumed, and then the classes should be separated by means. So if they're not, like maybe the two clusters, they don't have a separate mean, or by variance. There is another term called heterostochastic LDA that addresses these issues. So this is the last goal, this one. Yeah. Skedastic. Yeah, I don't know. Okay, we'll just go over it. It's the first and last. So I think we're done almost. Yeah, I think the prof will know this part better than me. I won't even attempt. But yeah, you guys learned the main part. CCA is the, it models the joint correlation between two sets of data. And we are like trying to capture their strength. It's like opposite of ICA. You can think of it like that. Okay. Yeah, I won't even attempt that. So, okay. If you have problems with your grade, just come to OH. We can fix it right there. But yeah, you guys can go and just look at the conclusion. LDA learns discriminative representations via supervision, and CCA and LDA are same when we're dealing with labels. So yeah.